Buenos studies. Thank you. That's really encouraging. This is my first few Spanish I learned. So today I'm going to talk about the analysis of the wider economic impacts of transportation project, investment project, infrastructure project using integrated land use transport models. So the presentation has the following parts of background, the literature review, study data and methodology, how we did it, and some results and recommendations, conclusions and recommendations. The first one is the development of transportation system of upgrading of transportation infrastructure unavoidably results in numerous alterations and the effects on the surrounding communities and the cities. So it will probably benefit some people, but provide, create some bad things to some people because of, there's noise, there could be the pollution, right? Air pollution, there could be accidents. So we want to do some analysis about this. Basically, these impacts mostly we talk about is from the economics point of view. There are basically two types. The first one is called the direct effects, like we provide the transportation system to move the people and goods efficiently, safely. The most obvious results would be the reduced travel time or transport time, right? And reduce the cost. So this is called direct effects. There are also the other effects, it's called the indirect effects. So enjoyed by the non-users of transportation facilities, and those can be enjoyed by the location of those activities, like the accessibility, the increase of accessibility, and the increase of the scale of economy and the productivity, those things. We combine those ones into one term. It's called the wider economic impacts, WEIs. We feel it's crucial to accurately analyze and evaluate WEIs in order to make the right decisions. Because traditionally, we, as engineers, transportation engineers, we really look into the travel time and transportation costs. But actually, transportation system plays a much more bigger role in the entire economy, right? So we need to show that to convince the people, convince the politicians to support our goals, like to make transportation system better. But if we want to do that, we need this, right? We need to show them the transportation system, transport system will not only reduce the travel time and transportation cost, it will also, provide much wider benefits to the people in the society. To date, there is no consensus of how WEI should be estimated, not to see the standard and guidelines. Some European countries already did some studies and provided some guidelines, like the UK and Netherlands. But for most of countries in this planet do not have any, guidelines or standards to do this. But it's kind of imperative to develop the methods for estimating and evaluating the spatial distribution of wider economic benefits. And because this really shows who better off, who worse off, right? So this is important. It's not just an aggregate number. Actually, it should be a number to different places. And more rigorous and consistent forecasting of, we can do this by integrated models, like integrated land use transport models. And this kind of approach we feel is they provide a more rigorous and consistent forecasting for spatial distribution of economic impacts of transport infrastructure. And they provide an important base for formulating investment plans for transportation infrastructure projects and land use economic development planning. Because you have those basically elements in your model, so you know who will gain, who will lose. That's important. And it has important practical and theoretical values, of course. This is we use National Waterway Project as a case study. Basically, we developed the method really to show to the provincial government this is worthwhile. So it's a big decision to the, to the provincial government because it will take like 100 billion yuan to complete the project. It's really a big project. So they want to know the bigger impact. It's not just reducing the transportation cost, right? What kind of a wider economic impact this water project could be. It's a national strategic infrastructure project to link the Pearl River with the Yangtze River to Jinghang Canal and most of seaports along the East Coast. So it's like this. So Beijing is here, Shanghai is here. This is my hometown, and the Guangzhou is here. This is like the major urban centers or the metropolitan areas. So the Yangtze River is all the way from west to the east, and the Pearl River is here. And what they want to do is they want to get this done, the big canal to go through the mountains. There are some rivers, existing rivers on each side of this canal. So if they can get the canal done, then all the river systems are connected. So they can move the goods much cheaper than before. So that's what they want to do. So this is the plan to invest about, my numbers are not so accurate. It's 68 billion yuan over the period of 7 years. Our WEI analysis covers both the construction and the operation period from 2035 to 2050. I quickly go through this. This is just what we did before we start this. We look at the literature. We found that those methods are there for economic benefits analysis of transportation investment. So this quasi-production functions, CBA, input-output models, spatial computing, general equilibrium models, and the one we use. Quasi-production functions is macroeconomic models, like the famous Cobb-Douglas function. It's really just consider the investment as a direct injection to the economy, a broader agreement on the positive contribution of transportation infrastructure to the overall economy, but it tells later about the actual mechanisms through which the benefits arise, especially from a particular industry and how that result in the ripple effect to all the other linked industries. CBE, this is the most popular, analysis models. Like traditionally, they use this rule of half model to just calculate the benefits. But it's a log sum method is getting more popular, or more scholars saying we should move to the log sum, because log sum will provide a much more scientific and scientific way to calculate this. It transfers the connectivity to accessibility to the location utility, like the improved accessibility. The traditional rule and a half is usually just consider the transport time saving or transport cost savings. It's only consider the direct effects, actually, the direct rather than indirect ones. It doesn't consider the wider economic impact or distribution effects and assume perfect computation. The input-output models, it use the general equilibrium approach, showing this is kind of improvement over the first one, production function. It's showing the inter-industry linkage is like on your right at the bottom. It's showing the linkage between the industries. So the inputs from which industry output will be consumed by the other industries. And this is a technique readily available, but they use fixed coefficients, so which imply that an industry structure remain unchanged, achieve equilibrium in supply, demand, in quantity only. So the fixed coefficients imply that the scale of economy, the substitution impacts, all those important aspects in the economy cannot be considered. And it's also cannot consider the special distribution of W, because it's aggregate tables. It doesn't tell you which part of the country or which part of province will receive the benefits, or this kind of model, this SCG, special computable general equilibrium model. There are scholars doing research on this. They have very strong macroeconomic theories, conformal better to macroeconomic theories, but that fact or that property also makes it difficult for engineers or the practitioners to use them and to understand them even. So because it's so theoretical or so theory oriented. And it also less powerful in representing land use and transportation than the integrated land use transport models in general. And it's very hard and time consuming to develop, because you have to encapsulate all those economic theories like a scale of economy, the substitution effects, all those into your model. That's a lot of work, and you got to be knowledgeable in economics, and then do this kind of model. So the more research work is needed. It's not really practical at this point of it. The last one, the one we use, there are a variety of the integrated land use transport models available, such as Urban Simplicus, Plan Trans, MUSA. So we want to use this to understand how transportation investment, like the impact upon land use changes, like the picture on your right shows the transport improve the accessibility, and then the land use start to, the value of the land start to increase, and then the being developed more, and then the activities will increase and all that, right? And then they bring the higher transport demand to the transportation system. It may not be, but this kind of models may not be conforming as better to the macroeconomic theories as CGE does. But I feel this is largely constrained by data availability. For example, the fixed technical coefficients to show the linkage between the industries. We have that in China at provincial level. We never have anything below the provincial level because that's require a lot of work, very detailed data to compile the input-output tables. You just cannot get these things at very detailed or geographic units. So it's not something we cannot do. It's mostly, because of the data availability, we cannot do a lot of fancy things as demanded by, economists. Like a scale of economy, can you find some places you have to do the survey and then to get the better technical coefficients by yourself? Usually you cannot do that. And it could be, those kind of data could be the business secret. You simply cannot get them. So in summary, the main problems with current research is the traditional method of evaluating economic benefits of transport infrastructure investment are incomprehensive in scope, insufficient consideration of the impact of land use changes, and the lack of the analysis of the spatial distribution of the impact. So there are still shortfalls. Mostly they just do it using transport models, like using the rule of half, and they only consider the transport time or cost savings. And of course, I talk about this, and the insufficient conformity to economic theories. The data and the methodology, I just quickly go through this. It's a lot of data we need. We need the, input-output tables. So luckily we have this ready because in China we have the provincial hour tables every 5 years. We have a few latest ones, and we have base year data about census, population employment, and we have remote sensing data. I talk about this for land use patterns. Of course, transportation network, and some big data like AIS. It's like for water transportation, each ship would have some GPS type device tell you where the ship went and how quickly it went. And some traffic volume counts, and some statistics mostly at the ports, the throughputs, and the others. We have the calibration and validation year data mostly at the network level and the land use side. We have, cargo related, like by this is usually the data we have is from the yearbooks, but they are usually very aggregated. We only have this at provincial level. We rarely get something at the mode or port level, but that one is by mode, but this is all usually at the provincial level. We designed this. This is like a blueprint of the model to showing how many activities you want to represent, how many goods, service, land, space, those commodities you want to present, and how they interact with each other. So in total, we have 26 type of activities, including 2 types of households. It's rural and urban. So we feel, in China, the urban households behave very differently with from the rural counterparts. So we have 2 types of households, 23 type of goods, because we want to model the goods in 5 categories, which is important for differentiated demand of different modes, especially between the highways and the railway and waterway. The railway and waterway tend to carry those bulk goods, but the highway tend to carry those higher value goods. Labor, land space, product, 3 transportation modes. Those are activities we represented. Actually, what we did is we did the opposite way. We determined the goods first, because we have statistics to show the major goods transported by 3 types of the transportation modes, and then we use that to look at which kind of activity we want to represent. So it's kind of reverse the design, and those are the land and space category, land categories we represented. This is the zones we developed. So it's inside the zones we use 99 counties or districts as the zones, and then the outer ones to represent the interactions with the other provinces. And those are, just some visualization of the base year data, the population employment. And this is the remote sensing data we have to show you where the woodland, agriculture land, construction land, and we did quite a bit of work to disaggregate construction land into 5 categories, like the residential, commercial. We use kind of a land census algorithm to do that. So this is the current land use and the forecasted land use over the different years. And this is a network we use. So the methods actually are not so, we only compare 2. The first one is input and output analysis. The second one is integrated land use transform models. The first one basically is like a benchmark. It doesn't consider a special distribution because it's aggregated tables. But second one will provide both aggregate numbers and then the distributions. We just want to use the RO analysis method as a benchmark. So this is the flow chart. I just quickly go through the methods. Probably it's the 2 methods could be a little bit complicated, but I just quickly go through this. So in construction period, we see the wider economic impact is mainly triggered by external investment. So basically the investment goes to the construction industry to build the canal, and then it will consume all the necessary, goods and services to do that. So our table will provide that kind of linkage to do the calculations. And then after the construction period, then there is the operation period. So the wider economic impact is mostly triggered by the transport costs reduction or saving, right? It's those ones is divided into labor inputs and the intermediate inputs. Our table of future years is predicted based on our table of the base years. There are some equations to look at the labor inputs and the total consumptions from the construction will be calculated based on this kind of equations. So the upstream or downstream industries, how they link together. For the integrated land use transport models, we use the PCAS framework again, and we use the following equations to calculate the consumer surplus or producer surplus, depending on which activity you look at. So for industries, usually we look at the producer surplus. For households, we look at the consumer surplus. And it's very simple. It's just the quantity of the first scenario multiplied by their location utilities minus the quantity of the base case or reference case multiply its location utilities. So basically the model gave us the location utility of a given activity and its quantity, and we just simply multiply and then derive the results. So basically the first one will calculate the utility of a given activity when the canal is built. But the second one is the business as usual, or there is no change without constructing the canal. We compare the two. We got the consumer surplus or producer surplus. So this is a framework I already introduced, talked about it yesterday, so I just quickly go through this. Basically, it has the 4 modules, right? From the top, there is economic, demographic, aggregate forecasting module, and then in the middle, there is activity allocation, space development, and then the transportation. It can do, relevant policies like economic, spatial planning, land use, space development, transportation, and sometimes environmental policies. This chart looks a little bit complicated, but it's really to show that we did a good amount of work. And on the top, there is no canal scenario, and then on the bottom, at the bottom is the waste canal scenario. And then we did the calculations and we compared them. That's it. This is a without canal scenario. We developed several technology options to be consistent with what we are going to use for the with canal scenario. And we also have the schemes built for different years to kind of simulate what's going to happen, especially on the for the highway network in the province. And this is how we develop the AEF. We use the input-output tables to develop them. And then we develop the technology option I. It's really the technical coefficients to represent the the linkage or the consumption production patterns of the industries. And this is a with canal scenario. The differences is here. It's the in the middle. It's the construction period. So there is external investment to go into the. It's about 68 billion yuan per year to the system, and we assume they're going to the construction industry, and then how would that create the impact to all the other industries. And then by it is built like 2035, so the entire system was, the magnitude of the entire system, it will be increased quite a bit, and we create another set of activity totals, another AEF, another set of technology options. So the difference is really, there is a construction of the canal, and then there are external investments to the system over 7 years, a significant amount of investment, and that really changed the system, so that we use this one to model the system. So this is what we did. So we assume 7% of total annual investment goes to the newly added capital for transportation. And we increase the volume of the activities added by investment to the out table for each year of the construction period. So balance the new AEF table. So this is after so this is how we create the new activity totals by considering this increased amount to the investment to the original activity totals we forecast without the canal construction. And then after the canal is built, there is operation of the canal. Then we assume that the cost of water transportation will be reduced by 25%. And then we recalculate the cost of transportation cost of the cost of transportation over the multi-modal transportation system, because we have the data like how each sector used railway, highway, and waterway. We recalculate the transport cost, but this cost is a kind of a weighted average over the 3 modes. And this is how we developed the network over the years. The base year 2012, 2020, by adding the new highway links, 2028 start to have the construction of Ganyue Canal, and then by 2035 we start to, so the canal will be used, and then we change the water network schemes to reflect that. Those are inputs. I already talked about. Mostly we change the technology options and the schemes to reflect the changes. We did some model calibration, like the mode choice, the freight shares, and we did some, calibration on the locations of activities, population, the goods trips, labor trips, and then we have the survey data to support the kind of the trip lengths and the trip distributions. The study results, I have to see the results presented here are kind of preliminary and subject to further changes. We're still looking at some minor issues. This is the forecast of the different sectors, the magnitude in terms of the dollar values or the RMB 10,000 RMB. Using the S curves and the moving averages I talked about yesterday. And with canal scenario, what we did is we used the investment to bump up the size of the system. So you can see actually there are two curves. The blue curves is under the scenario without the canal construction, but the yellow ones, the yellow ones is orange ones is really the scenario to simulate the size of a given activity under the scenario with the construction of the canal. And for this metallic minor processing activity, we found it never used the water transportation, so the investment to water transportation won't have any impact to it. And for the other ones, you can see there is a very obvious difference between the two scenarios, between the sides under the two scenarios. And then we have some results. So this is for our table results, and we can see, we can do the analysis over different sectors. So the A16 will receive the highest benefits, and then the others follows. Again, we can do this by year, 2031, 2042, by sector, and then how it's look like by years and the numbers. So those are the numbers. During the construction, it's like 85.6 billion RMB per year, the wider economic impact. Over the operation period, it's like 110 billion per year. And for the integrated land use transport model, we know it's better because it can tell you the spatial distribution of the benefits. So compared to our tables, because we have the zones, we have the areas to represent it, and we can show you like over the time and the space how the distribution is. So we'll have a greater impact for A15, right, in those cities, and for A16 where the benefits goes, A19, and for distribute to different activities. And this is basically the comparison of the two. You can see actually what the Picas model predicted are always higher than those reported by our tables, because our tables cannot consider those special effects, like the effective density or the scale of economy, because Picas has some ways to kind of simulate that a little bit. So the Picas model always produce higher numbers than our tables. The rate of return at the bottom show you it's like 41 times 41. It's very high. That means for each dollar you invest, you will receive like 41 times benefit, the $41 back. Actually, that's very good. We need those numbers to convince the public and the for anything we do in China and for anything we do in Costa Rica as well, right? It's not just we save the transport time and the cost. Actually, this kind of project will have much wider, economic impact. We have rigorous tools to show you that. This is very convincing to a lot of people, I think. This is the conclusions. So the investment to the construction of the Ganyu Canal will bring significant WS to Jiangxi province. Actually, we only consider the investment made by this particular province. The other province, Canton province, will provide another like 100 billion something. So the rate of returns is very high at the constant prices in 2028. Following industry will receive the highest benefits. So we feel the WEI's analysis of transportation infrastructure investment using Pickett's model consider development of economy because we can forecast the magnitude or size of the different activities in the future, the land use changes, the impact of demographic employment changes, and the special crossing effects of industries. So we feel it's an important tool for decision makings. I already talked about this. So we highly recommend to use integrated models to do this kind of economic appraisal of the transportation infrastructure investment. That's it. Pura vida. Pura vida. Thank you.
Muchas gracias. Muchas gracias, Mr. Zhong. Y bien, tenemos dos consultas que nos llegan a través de nuestra herramienta, que les recordamos es Slido, y estaremos proyectando el código QR para que lo tengan por ahí presente. Y bien, la primer consulta que nos llega a través de nuestra herramienta dice: ¿qué estrategias de convencimiento sugiere para que los líderes de las municipalidades empiecen a recolectar datos?
Sorry, I got part of that. Can you repeat a little bit?
Yes. ¿Qué estrategias de convencimiento sugiere para que los líderes de las municipalidades empiecen a recolectar datos?
Data for modeling?
Yes.
Oh, okay. I guess, the investing to modeling appears to be not beneficial to a lot of politicians because it takes time and you don't get visibility needed to the public. But experience from a lot of places show that it will provide a long-term, return, by really looking into the decisions seriously and scientifically. You will be able to use money wisely and allocate the resources smartly. So I think from that point of view, we should, as an engineer, we should, fight for that to convince the politicians to invest into the data and the modeling.
Okay. Y bien, tenemos una última consulta que les invitamos también a realizarlas para los siguientes expositores a través de la herramienta. La consulta dice: ¿cuáles perfiles profesionales o carreras recomienda que participen de los equipos de investigación y análisis como los expuestos hoy?
Okay. Ideally, we need an economist, an engineer, and a geographer. I mean, it's it's kind of interdisciplinary work. We do need, in this presentation, you can see we actually have to work with the remote sensing data. We had a lot of problems with the GIS software, so to process the data to make sense and all that. So we at least need a few transportation engineers to work with one economist and then one geographer, those kind of things. So should be from multiple fields, a team from multiple fields.
Muchas gracias, Mr. Zhong. Bueno, le damos un caluroso aplauso entonces.
Thank you.
Y gracias por acompañarnos. Pura vida.